Hello, welcome everybody. So, the last two lectures we have discussed about the concept of mass balancing and some applications with some numerical examples. In this class, I would like to extend that into a very important topic in Mender processing, that is called the closed circuit grinding, and here I would like to show you that how you can apply the concept of mass balancing for various purposes. But before I go to the numerical examples, let me explain a bit about closed circuit grinding. We have already discussed it during hydrocyclone operation, or say during the topic of hydrocyclone, and during the ball mill operation or grinding in general. Even closed circuits, we discussed about closed circuit crushing, but here I will give more emphasis on closed circuit grinding. So, why we give more emphasis on closed circuit grinding? Because the grinding circuits carry responsibilities that can have impact on all phases of the operation, like the grinding circuit, because of the most of the metalliferous ores and the other lean grade ores like platinum group minerals, like even for gold, minerals like gold, they are day by day, its quality or the assay content of the ore is deteriorating. So, the liberation, because of that, the liberation size is becoming finer and finer. So, for that you have to make the entire ore to be ground precisely to a very fine size, and for that depends on the efficiency of the grinding operation, and grinding operations mostly that quality control is through a classifier, that is a hydrocyclone, and that is why I am writing this, that is it carry responsibility that can have impact on all phases of the operation, including efficient mill operation and successful production, with an aim to closely control the product sizes. Because if the product sizes, that is if they are not liberated properly, or they are liberated at a too fine sizes than what it requires, then it will have adverse effect on the downstream process, and normally what is froth flotation process. If a mill does not grind properly and produces either coarser, that is under grinding, or finer over grinding products, then it will have adverse effect on the downstream process operations. Because if it is too coarse, then also downstream processes will have operation, because the material is not properly liberated. If it is too fine, it will create problem with the slurry rheological aspects. So, the proper grinding operation is required from both economic as well as process efficiency point of view. And if the material is ground too fine than what it is required, unnecessarily we will be wasting much of this energy. If the material is removed from the mill, as soon it is ground to the required size, over grinding can be eliminated or minimized. But as I said, that it is impossible to know that whether my grinding mill has produced the desired size or not, if we do not have a classifier, that is a hydrocyclone. So, this operation, that is when we have a hydrocyclone and a ball mill, or as a grinding mill, or maybe another mill, we call it a closed circuit grinding operation. That is, we are having a quality control check through the classifier of the product fineness. Closed circuit grinding consists of one or more mills discharging ground product to classifiers, which in turn return the coarse product from the size separation back to the mill for further grinding. That is, we have already discussed it, that you have got a mill or you may have a series of mills, and the products, that is your overflow, that is your what is coming out from that in the form of slurry, we are sending it back to a classifier to check that whether my particles are ground to the desired size or not. Definitely it will be ground to that desired size. So, whatever the materials are, whatever the particles are ground to that finer sizes, we are taking it out from the circuit through the cyclone overflow, we are sending it to the downstream processes. It may be your gravity concentration process, it may be your magnetic separation process, but usually it is the flotation process. And the material which is coming from cyclone underflow, that we send it back to the grinding mill for further grinding it. In this circuit, grinding efficiency is very much dependent upon the size separation affected. So, care should be exercised in selecting the type and size of classifier used to close the system. That is what is the importance of selection of appropriate design of a cyclone is important. This type of grinding is the most common circuit found in mineral processing facilities, mainly because a lot of ores and product requirements are not suitable for open circuit grinding, because most of the cases you cannot guarantee. So, we hardly use open circuit grinding these days, because you need to generate very fine sizes of particle as your liberation size demands. So, what are the advantages of the closed circuit grinding? One is, that is, this arrangement usually results in higher mill capacity. How? No, because you do not have to give more than the required residence time inside the residence time of the particle inside the mill. So, what we can do, that is material going in the form of slurry into ball mill. So, you can run the mill at a much faster speed, so that your capacity increases, but you have got a quality check. So, what will happen now? You are just optimizing the grinding time, because I am sending it back the material which is not ground to that your desired fine size, I am recycling it back. So, that is what you are using the higher mill capacity and lower power consumption per ton of product, because you are doing exactly, you are grinding it to, you are minimizing the over grinding phenomena into a grinding mill. It also eliminates over grinding by removing fines early. It avoids coarse material in the final ground product by returning this material to the mill. So, in essence, you are controlling the product quality also. There is a schematic of your common grinding circuit mill, that is your, say suppose you have got a feed, that is your new feed plus circulating load, and that feed material, why you are sending it to a cyclone? No, first you want to take out, because my feed which is coming from my crusher, suppose I want your 40 micrometer particle, that is my grinding mill is supposed to grind my material 100% below 40 micrometer, but that is the particle which is getting in here, that may be around your say 10 millimeter sizes, but that is coming from your crusher, that is a tertiary crusher, maybe upstream, but that crusher may already have produced some portion of minus 40 micrometer particle. So, why to send it directly to a ball mill if that is the situation. So, why do not we send it to a hydrocyclone first to take out the already ground product what is there in the feed. So, that is why there is the your new feed and plus the material which is being your already not ground, not finer than the your desired size, that is the circulating load. So, new feed plus circulating load, first you are sending it to cyclone and again you are checking that whatever the finer material is there, finer means you have decided that I need to have a 100% or 95% below 100 micron size. So, whatever material is below that size, I am taking it out and the remaining is coming through underflow, that I am sending it to a ball mill, and the ball mill product as a circulating load I am feeding it here. So, you have got now a circulating load plus your fresh feed, that is the new feed. So, although closed circuit grinding offers many choices for arrangement of the equipment as well as combinations of equipment, some of the more common circuits are, that is your rod mill classifier, that is you can have a rod mill and then you can have a classifier. The another orientation of this, it could be, that is you can feed here the material and the product discharge can go to the hydrocyclone, and then you are taking out the material whatever is already ground to that size and through the overflow, and that your undersized product, that is your whatever the material is coming relatively coarser material through the cyclone or underflow, that you can send it back here. So, that could be the circulating load in that case. So, it could be a ball mill classifier circuit, it can be a rod mill ball mill classifier circuit, it can be a rod mill classifier, that is you have got a first coarser grind, then you are checking it, that is you can have a classifier, then you can have a ball mill and then you can have another classifier. That means, you are controlling the sizes of the particle at each stages. Classifier separates the feed material into two fractions, that is fine or undersized material and coarse or oversized material, because classifier in this case is hydrocyclone, again and again I am mentioning that. Oversized material is returned to the same grinding mill, undersized material is the finished product for that circuit, it is being sent to the next your downstream processes. The tonnage or weight flow rate, that is your tonnage or weight flow rate of the overflow or undersized solids of a classifier, that is how much of material is going out through the classifier, is always equal to the tonnage or weight flow rate of the solids fed to the grinding mill in a closed circuit grinding operation under steady state conditions. It is a very vital statement. So, what is happening? You are feeding a material suppose at 100 tons per hour and you are, when you are starting it, that is 100 tons per hour your fresh feed you have started with. Now, what will happen? Now, only 40 tons per hour of fines you are separating out. So, how much you are getting it in the underflow? That is 60 tons per hour. So, next one, but you can only feed total 100 tons per hour. So, 60 tons is your recycled feed. So, the fresh feed next one, next step you can only feed only 40 tons. So, that is 40 plus 60. So, that is your 100 tons. So, 60 is getting recycled back. So, what this statement is saying, that your amount of fresh feed is equal to how much of fines you have taken it out from the circuit. Other remaining portion will be recycled back. So, this is the circuit I was talking about, that is you can have, I have shown you one circuit, that is you can make it, that is if I have your fresh feed some particles which are already finer than that, I can have a orientation like this, that is first feed can go to the cyclone and then it can be recycled like this way. And most common one is this one, that is you have got a new feed and you are sending it to a mill. It may be your grinding mill, any grinding mill. Then the product from this grinding mill, you are sending it, you are feeding it to a classifier, that is a cyclone. That overflow, which is already finer than sizes than that what you desire, that is you are taking it out. So, remaining the coarser material, you are just sending it back along with your fresh feed, and then the total, that is your, this is called the circulating load plus your new feed, you are sending it to the grinding mill. Now, my grinding mill operation is basically will have the best performance when the your at a fixed or at a consistent your percentage solids, that is contained. So, I have to check it, I have to calculate it, that how much of is that circulating load. So, I can control that what should be the new feed, so that there is no disturbance in the relative percentage of solids and water as well as the total charge, that is your volume occupied by the total charge, where you have got the steel balls. In many cases you may not have balls, it may be ag mill or it may be sag mill, relative percentage of your balls may be less, but the total volume of the charge you cannot change. So, the balls you are not changing, water and your solid you should have a typical percentage. So, you have fixed it that my mill should be working at a 50% solids by weight. So, you have to maintain that, otherwise the performance of the mill will be deteriorated. So, the circulating load, how do I calculate? Circulating ratio, before we calculate go for circulating load calculation, let me define you another ratio, that is what frequently used, that is called the circulation ratio. It is represented at capital C R. So, circulation ratio is defined as the ratio of the flow rates, of the circulating stream to the flow rate of the new feed to the mill, which at steady state is equal to the fine product leaving the circuit. That is what I have already explained you. That is, how much is the ratio of the flow rates of the circulating stream to the flow rate of the new feed to the mill, which at steady state is equal to the fine product leaving the circuit. Okay. So, CR, that is, here you see that is the new feed, that is the Q, and this is the overflow fines is designated as Q, and underflow, that is the coarse material, is designated at T. So, then CR is equal to that T by Q, that is what is that your ratio between the flow stream to the flow rate of the new feed, the ratio of the flow rates of the circulating stream. So, what is the flow rate of the circulating stream? That is the T, that is whatever is coming from the cyclone underflow. So, that is the circulating stream. So, that is the capital T, and what is the fresh feed? That is the fresh feed to the mill is Q. So, that is the new feed or the fresh feed. So, it is T by Q into 100. So, CR is the ratio between the circulating load divided by the fresh load, that is T by Q into 100. So, circulating stream in a closed circuit grinding at classification circuit, that is what is shown here. Now, let us see that how we can apply this concept of circulating load ratio, or how we can calculate this. Then I will show you that in combination of this circulating load ratio and the mass balances, what we have learned so far, how we can apply to mass balance a particular system. So, this is a problem, that is, if we consider a separation of feed into underflow and overflow by a hydrocyclone, that is, if we consider that we have got a hydrocyclone and you have got a feed, and that gets separated into two products, underflow and overflow. Feed is 1000 tons per hour and the underflow is 70% of the feed. Determine the circulating load. So, what should be the circulating load? Now, in the hydrocyclone underflow is recirculated, that is the underflow what is being recirculated. So, the recirculating load ratio is mass recycled divided by fresh feed. So, now if I do a material balance, so 70% of the feed is underflow means mass of underflow is 70% of 1000 tons is 700 tons. So, remaining 300 tons, because it is in steady state, it has to go to the overflow. So, the mass of overflow is 300 tons, right. So, what will be the fresh feed? So, that is the 300 tons which is taken out from the circuit on a hourly basis, it is 100 tons per hour. So, every hour we are taking out 300 tons of material from the circuit. Now, to maintain that 1000 tons, so that means every time 300 tons per hour is the fresh feed. So, that is why I said that how much of fines, so that is the overflow is taken out per unit time is equal to the amount of fresh feed. So, now what is the recirculating load ratio? That how much is the mass of underflow, that is 700, and what is the amount of fresh feed? So, that is 700 by 300. So, that is equal to 2.33. So, that is how we can calculate the recirculating load ratio. Now, you see that another problem. A ball mill receiving 100 dry tons of new crude ore per hour, that is your fresh feed is your 100 dry tons, is in operation in closed circuit with a classifier, right. So, the percent solids by weight in the feed to the classifier, that is the percentage solids by weight in the feed to the classifier, in the classifier overflow, that is the fines, and sands, that is the coarse fraction, are 50, 25 and 84 respectively. So, the percent solids by weight in the classifier feed is 50%, in the classifier overflow it is 25%, and underflow it will be much more concentrated because you have less water. So, it is 84%. Now, I want to calculate the circulating load. So, what is given? You are given with the fresh feed, that what is 100 dry tons, and your percentage by weight of the cyclone feed, underflow and overflow is given. How do I calculate? So, that means this is the circuit, that is you have got the feed, that is 100 dry tons, and that is the mill. So, you have got a classifier, that is a hydrocyclone. Now, you have got a overflow and you have got an underflow. So, this one, that is at what rate it is going. So, this one is 50% solids by weight. So, that is the ball mill discharge. Okay. So, that is the mill discharge. Overflow is dilute, that is 25% by solids by weight, and underflow is 84% of solids by weight. I need to calculate the circulating load ratio. How do I do it? Here I have to use the concept of mass balance also. So, the closed circuit grinding operation is shown in this way. So, whenever you are given this type of problem, it is better to draw the circuit, so that you do not have any confusion. That is what personally I also do. So, the fraction of solids in feed, that is feed to the classifier I am talking, that is 50%. So, that is we have to convert it into fraction, because we are balancing it through the fraction. So, it is 0.5. Similarly, fraction of solids in overflow is 25%, that means it is 0.25 and it is 0.84 the underflow. In a closed circuit operation, so new feed is equal to, we have already said that what is the new feed, what is the fresh feed. So, this is the total feed, that is the new feed plus your recirculated feed. So, your new feed is equal to product, that is equal to 100 dry tons per hour. So, that feed is equal to, the new feed is equal to 100 dry tons per hour. So, the new feed means that is the 100 dry tons per hour. So, here, so we are sending out, we are taking out 100 dry tons of that solid per hour. So, total weight of overflow, that is you have a 0.25, that is your 25% of solids by weight here. So, how much is the slurry here? How much is the slurry that I have to calculate? So, the total weight of overflow is water plus solids, that is your pulp is equal to 100 by 0.25. So, that is 100 tons you are taking it out, and that is equal to 25% of the total material. So, what is the total slurry I am taking it out? So, 25% is equal to 100 tons. So, 100% is equal to 400 tons per hour. So, we get the value of total weight of overflow is 400 tons per hour, right. I hope it is clear to everybody. Now, so if we assign that capital F is equal to weight of feed pulp to the classifier, I do not know how much is going there into the classifier, and U, capital U is the weight of underflow pulp from the classifier. I do not know also this U, that how much is going there, because I only know that this is 400 tons per hour. Okay. That is total, that is solids weight plus water weight. So, what I can write, that is total pulp solids plus water balance equation is F is equal to P plus U. We have already learnt it, that is total feed weight is equal to total weight of your overflow product and plus your underflow product. So, P we have said that this is the product weight, suppose. So, that is equal to 400 we have already calculated. So, we can write that F is equal to P plus U. So, F is equal to 400 plus U. I do not know what is the value of F and what is the value of U, and that is what I want to solve. Now, I can use that mass balancing formula based on the dry solids balance. So, what is that equation? The dry solids balance equation is F F, if F is the fraction of solids by weight in my feed. So, that is F F is equal to P P plus U U, and we know the solid percentage. So, we have already converted them into fraction of solids by weight, that is F into 0.5 is equal to 400, I know that is the capital P, and this is 0.25, that is small p is 0.25, because we already said that your overflow is having 25% solids by weight. So, that is 400 into 0.25 plus U, capital U into 0.84. So, now you have got two unknowns F and U, you have got two equations. So, easily we can solve it for we can easily solve that. How we can solve it? Now, we can put the value of F here in this equation, that is 400 plus U into 0.5 is equal to that. So, we can find a value of U is equal to 294.12 tons per hour. Again I am requesting everybody that please do these calculations on your own, otherwise you will have your concept will not be clear. So, when we solve this, that is by putting the value of others in this equation, we get a value of u is equal to 294.12 tons per hour. So, now the circulating load is equal to, I have to calculate that what is the circulating load. So, circulating load means what is the solids coming out from this underflow through this cyclone underflow. So, that is the solids in underflow. We already know that has got 84% your solids. So, the circulating load is, that is the total your slurry. So, weight your water plus your solid. So, that will be 0.84 into 294.12. So, that is 247.1 dry tons per hour. So, that is your 247.1 dry tons per hour of solids in the underflow. So, percentage circulating load is equal to circulating load by new feet into 100. So, what is the circulating load? It is 247.1 divided by new feet is 100 into 100. So, it will give you 247.1%. Now, here I want to explain that what is the meaning of this circulating load. Suppose in one case my circulating load is 500%. What do I do? So, in that case maybe the product quality we are assuring, but your capacity of the mill will be drastically reduced, because you are having almost 5 times the fresh feed, that is the recycled material. So, your fresh feed, that will dictate that at what rate you are processing the entire your meal, how much is it capable of accepting the new feed. But if your circulating load is 0, so that means your cyclone is not properly separating that. It is impossible that your grinding mill is producing 100% finer than material what you desire. So, this is also again a measure, that is the circulating load will also give an idea that whether my circuit is performing well or not, and it is the it depends on the what type of material you want and what type of what is the degree of accuracy you want in your product quality. Based on that you decide that what should be the ideal percentage circulating load. And this example basically tells you, that is how do I use my mass balancing equations even to have a control or to have some measures, that is for optimization of my closed circuit grinding operations, and even for any mineral processing circuit. If you know, if you apply this mass balancing equations, you can know the clearer picture, that is whether you have to take any action or remedial measures for improving the performance or not, or you may be convinced that okay, my mill is or my entire plant is working at its best operating conditions. That is why I said that mass balancing helps in process control, in optimization of your say entire mill, entire your mineral processing plant. This application of this equation may be little bit complicated when suppose you are processing lead zinc ore. So, in this case your wanted material may be 3-4 different materials, that is you can your lead may be your wanted material, copper may be your wanted material, zinc could be your wanted material, and you have got number of unit operations. So, there you can, if you know how to apply the two product formula, and then you can say apply this formula for each particle classes and or say each material of your interest, and then you can derive the formulas for even some multi product systems, like many times you have 3 product from coming out from a circuit. So, I do not want to in this introductory course, I would like to stop here related to the topic of mass balancing. I hope you have understood it. Thank you very much.